So in this lesson, we're going to be learning how to complete the square, which is an Algebra 2 topic that in the Big Ideas textbook is in section 3.3. The goal in completing the square is to make a perfect square trinomial. In case you're not sure what that is, a perfect square trinomial, for example, would be x minus 3 times x minus 3, or x minus 3 quantity squared. It's a perfect square because it's the same factor twice. So you could write it as x minus 3 times x minus 3, and we could expand this by foiling. You may have heard that term, which would be distributing the first, outer, inner, and last terms in each binomial. Or we can fill in the boxes in this nice little organizer up here. And so that's the one I'm going to do for you now. X times x would be x squared, and then I would take x times negative 3 is negative 3x. Negative 3 times x is also negative 3x. And then negative 3 times negative 3 is a positive 9. So if I multiply that all out, I have x squared minus 3x minus 3x plus 9, which simplifies to x squared minus 6x plus 9. This one is expressed as the trinomial because it has 3 terms, whereas the x minus 3 quantity squared is expressed as the square of a binomial because the x and the 3 make a binomial with the 2 terms there. So this is an example of moving forwards in creating the perfect square trinomial. And what we're going to be doing in completing the square in this lesson is trying to move backwards when we're missing a couple of the parts. Here's what I mean when I say I'm working backwards. This first question says, find the value of c that makes x squared minus 6x plus c a perfect square trinomial. Then write the expression as the square of a binomial. Well, this would be the simplified version of standard form, which means x squared would go in the first box. The negative 6x must be what I got from these diagonal boxes, which means that if I split it to make it the same factor twice, I would have to split the 6 exactly in half and make that negative 3x and negative 3x. And I would be looking for the terms that would go on the outside that would make this square work properly. So x squared would have to be x times x. Once I have that, well, x times what up here would be negative 3x, and I can see that that would be x times negative 3. Similarly, negative 3 would have to go in the other blank, so that x times negative 3 is negative 3x. And so using that, I can figure out that the number that must go in this last box would be negative 3 times negative 3, which is positive 9. 9 is the number that completes the square. So now you know why the topic is called what it is. X squared minus 6x plus c. Well, if c is 9, then this turns into x minus 3 quantity squared, which was the goal. So I hope that makes sense. C is 9 in this case. That makes this a perfect square trinomial, and we can now express that as x minus 3 quantity squared. There are 2 main objectives when we use completing the square for now. One is just to complete the square to write a function in vertex form, and the other would be to solve a quadratic by completing the square. So in the first, we have an equation with x and y, or x and f of x. And in the second, we just have x and 0, right? They don't look quite the same. The second type only has the one variable. So we'll just do them one at a time. In the first example, to complete the square to write it in vertex form, I'm going to start by writing out a template with some blanks in it so I can keep myself organized. And I'm going to use the x squared plus 10x to complete the square, just the first two pieces, like I did in the last slide. And so I'm going to put a blank for the number that is going to complete the square. And then I'm going to write the -3, because I can't forget it was there. And then I'm going to write another blank after that. You'll see why as we do the problem. So if you want to draw the box, that's fine. If not, you don't need to, if you can kind of see what the pattern is. So if the x squared goes in the first box, I'm going to take the 10x and split it in half and make 5x and 5x in each of the diagonal boxes. And then I must have x times x along the top and the left. And then this top row would be completed by a 5, as well as the column would be completed by a 5. And 5 times 5 is 25. So 25 is the number that completes the square, which means if I had a plus 25 right there, then this part of the function would make a perfect square trinomial. So I'm just going to put 25 there so that I can make that perfect square trinomial. But the deal is that we can't just add 25 to the function because that changes the function, it changes the expression obviously. So we're going to just balance that out or compensate for that by subtracting 25 right after it. This is on the same side of the equal sign. I'm just adding 25 and subtracting 25. And the y equals is over here. I just didn't even mess with that for now. So then, on my first three terms, the x squared plus 10x plus 25, that creates x plus 5 quantity squared. And then the -3 and the -25, I can combine like terms to get -28 there. So if I wanted to write the function in vertex form, I have the x plus 5 quantity squared, and then I have the -28. And this is the function rewritten, but from standard form into vertex form, which means I can now answer lots of questions about the vertex of the quadratic as well and the axis of symmetry. In the second example, we don't have a y equals here. We just have a function that we have to solve, a quadratic to solve by completing the square. The steps are almost exactly equal, but then the solve by completing the square has a couple extra steps at the end. So I'm going to start by rewriting the first two terms. Those are the terms that I use to complete the square. I'm going to put my blank, and then plus 4, and then another blank. And I'm just working with the expression on the left-hand side. I do know that this equals 0, and if I wanted to continue writing equals 0, I could. But I'm just going to work with this expression first. So if I made the box, which is up to you, then x squared would go in the first box, and the -2x would be split into -1x and -1x. So this becomes x minus 1 and x minus 1. -1 times -1 is a positive 1. So positive 1 or plus 1 is the number that completes that square. But if I'm going to add 1 to the expression, then I should probably subtract 1 as well, so that I can compensate and not actually change what that left-hand side said. And now, I can write this in vertex form, that x squared minus 2x plus 1 becomes x minus 1 quantity squared. Right? That was what I did when I completed the square. I got x minus 1 times x minus 1. And then I have a plus 4 and a minus 1. So that's going to create plus 3. Equals 0 has always been there, right? So I don't really want to forget about the equals 0, I just wasn't concerned with it when I was completing the square. From here, because I have vertex form, I can solve this now by getting the perfect square by itself and taking a plus minus square root. So if I do that, I get x minus 1 quantity squared equals negative 3. And for us, we look at that and we say, well, if it's squared, how can it be negative? So that would be actually a no solution problem. We might revisit that at a later date and have some more interesting things to talk about that. But that would be as interesting as that's going to get for right now. We have a couple extra problems now, a couple special cases that are going to be a little bit more work. So I have 3 special cases. Completing the square is going to work best when A is 1, and B is even for ax squared plus bx plus c, that quadratic expression. And you'll see why here in just a second. If I go to complete the square with this x squared plus 5x plus 7, you may have noticed if we're always splitting that middle term in half, well, splitting 5x in half now creates a fraction, or a decimal, but we're going to do it with a fraction so that we can not have to use a calculator. So I end up with x squared here. Half of 5 is going to be 5 halves. So 5 halves x in each of the diagonal boxes, which means I would have x times x, and then 5 halves on the outside here. And so the number that completes the square is going to be 5 halves times 5 halves, which is 25 divided by 4. So I'm going to go ahead and rewrite this. I would get x squared plus 5x plus 25 fourths. That's the number that I need in there to complete the square. Plus 7 minus 25 fourths. That's what I'm going to stick to even it out. That is going to equal 0. And so the first 3 terms connect. Let me read that backwards. There you go. The first 3 terms are going to produce x plus 5 halves quantity squared. Now I'm going to need to combine those last 2 like terms. So when I'm looking at the 7 minus 25 fourths, well, I know that 7 is 28 divided by 4. So I would have plus 28 divided by 4 minus 25 divided by 4. And so this is x plus 5 halves quantity squared plus 3 fourths equals 0. So the last example, when we got a negative for a square, we just said no solution. I was only solving that one over the real numbers. But in 3.2, which was the section before this, we did learn about imaginary numbers. So this one we are going to go ahead and solve all the way, solve over the complex numbers. So this is going to become x plus 5 halves quantity squared equals negative 3 fourths. And now that I have it written as a perfect square, I can take a plus minus square root of each side. So I'm going to give myself a little bit more room. That was all the old stuff, and now I can continue. I would end up with, if I take a plus minus square root of each side, x plus 5 halves equals plus minus square root negative 3 fourths, which is plus minus, and then let's go ahead and deal with each factor separately. So the square root of -1 is I. The square root of 3 I can't do anything with, so I'm just going to leave it put. And the square root of 4 is 2. So I have this x plus 5/2 equals plus minus I times the square root of 3, all divided by 2. So to solve for x, now I'm going to be subtracting 5/2 from each side, and I would get x equals -5/2 plus or minus I root 3 over 2. We can separate that into -5/2 plus I root 3 over 2 and x equals -5/2 minus I root 3 over 2. To write it separately, or you can leave it with the plus minus if your teacher allows that. And then that would be our answer, taking into account the complex numbers, which I did not do on that last example. Another tricky part of completing the square would be if a is not 1. So the last example had b not even, and this one has a is not 1. So in this case, a is 2. There's a couple extra steps in this case. I'm going to factor the 2 out of the first 2 terms. I don't really care about the 11 anyways, it's just in the way. I have to deal with it, so it's still here, still hanging out. But I wasn't going to use it to complete the square anyways. So I'm going to take the 2 just out of the first 2 terms. And then I'm going to complete the square with just the part in the parentheses. So x squared plus 6x, let's do it without drawing the box this time. I know that I would split it into x plus 3 times x plus 3. So we're taking half of the 6 to get the 3. And then if I'm squaring that, then the fourth term in the square would be 3 squared, which is 9. So 9 is the number that is completing the square. Here I did half of 6 is 3. And then to get the 9, I said 3 squared was 9. Those steps are the same in all of the problems. This is just instead of drawing the box. So this is going to be 2 times x plus 3 quantity squared, if I can finally figure out what that I need to do to compensate for the fact that I just stuck a plus 9 there. In adding 9 there, normally I would just say minus 9 right after it. However, because of the 2 on the outside, by putting a 9 there, I've actually added 18. So to compensate for that, I'm just going to subtract 18 over here. So I get 2 times quantity x plus 3 squared minus 7. That's what is going to equal 0. From there, I'm going to solve it the same way I solved the last one. So I can take 2 times quantity x plus 3 squared would equal 7. So x plus 3 quantity squared would equal 7/2. And then I can take a plus minus square root of each side. So x plus 3 would equal plus minus the square root of 7/2. That's not rationalized, so let's go ahead and rationalize it. That's going to be the square root of 7 divided by the square root of 2, and I'm going to multiply by root 2 divided by root 2 to get plus minus root 14 over 2. So x equals -3 plus or minus the square root of 14 over 2. If I split that up into 2 answers, that would be -3 plus the square root of 14 over 2, and then -3 minus the square root of 14 over 2. So not terrible, but we've got to remember that if we're putting a plus 9 there, that we're actually subtracting 18 to compensate. And similarly, in this case, this is also a is not equal to 1, a is negative 1. I have two options here. If the goal was to put this in vertex form, then I must factor out the negative and leave it there. However, if the goal is just to solve, as the directions say here, I could actually multiply both sides of this equation by negative 1 to get x squared plus 8x plus 11 equals 0. This will produce the same answers, although it's not the same function. If I were to graph this, if this equaled y, it's not the same function. It would have the same x-intercepts, so it would have the same answers to the problem. If I want to do it without getting rid of the negative, then I would factor out the negative the same way that I would factor out the 2 from the last problem, and that would turn this into a positive x squared and a positive 8x, and then I'm just going to leave this hanging for the number that completes the square, and then stick the minus 11 on the outside. I'm not changing the sign of that one because I didn't put it inside the parentheses. So the number that is going to complete the square, if I just look at the x squared and the 8x, I know that half of 8 is 4. So that's the number that's going to go there, is that I'm multiplying the 8 by a half. And then 4 squared is 16. So 16 is the number that completes the square. But because of the negative 1 on the outside, by putting a 16 there, I actually added negative 16 to this expression, or subtracted 16. So to compensate, I would add 16. It's a little bit backwards of the way that we've done it in the past, because even though this term is a plus 16, the negative 1 on the outside made this a little bit more of a screwy problem. So I've got negative quantity x plus 4 squared plus 5 equals 0. From there, let's add the x plus 4 quantity squared to each side. So I have 5 equals x plus 4 quantity squared. Then I can take a plus minus square root. So plus minus root 5 equals x plus 4. And then I can subtract 4 from each side and get negative 4 plus or minus the square root of 5 equals x. I would end up with the same answers if I had divided the negative 1 from the whole equation, but just did it this way to hopefully reinforce to you that if this was equals y, and we were just rewriting it, that we wouldn't have that option there. The last thing that we're going to look at is just a secondary use for completing the square. Standard form of the quadratic function and vertex form of a quadratic function is something that you should be familiar with by now. So if I give you standard form and I ask you to write it in vertex form, or to find the vertex of the quadratic, we now have two ways to do the problem. The first way you've already learned is that from standard form, that the vertex x coordinate is x equals negative b over 2a. Well, in this example, that would mean x equals negative 8 over 2 times 1, which would be 8 divided by 2, which is 4. So I know that the vertex is 4 something, and I can find the y-coordinate by substituting 4 into the function. So that would be 4 squared minus 8 times 4 plus 11, which is 16 minus 32 plus 11. So that's negative 16 plus 11, which is negative 5. Then I can write the quadratic in vertex form by saying the a value, which is 1, is going to remain the same across all 3 forms, or all of the forms that you've learned. So this is going to be y equals 1 times x minus 4 quantity squared minus 5. That would be vertex form, and then what is the vertex is this 4, negative 5. So I actually wrote the form by finding the answer to the problem first and then going backwards to put the equation in vertex form. that will certainly suffice, and for some of you that might be faster. However, now that we know how to complete the square, we can complete the square pretty quickly to put this in vertex form, and then find the vertex from there. So in this case, I'd say y equals positive x squared minus 8x plus 11. And then once you get used to this completing the square thing, I want to show you this is how fast it's going to go. Half of -8 is -4. -4 squared is 16. So this would be a plus 16 and a minus 16. And 11 minus 16 would be -5. And so then that's all the work that I need. And look, I've got it in vertex form already, which is way faster than doing -b over 2a. And now from here, I can take and just read from vertex form that the vertex must be 4, -5. So you don't need to draw the box every time in order to complete the square, especially if a is 1 and b is even, then that's when you would want to complete the square. I hope that you've enjoyed this and this helps you in your mathematical quest for knowledge.